Okay, so before we start, how many of you have heard of singing voice synthesis? How many of you have actually used one? Good, good. Okay, so the technology, singing voice synthesis has advanced quite a bit in recent years. It actually gone realistic enough to be used for actual production. And by production, I mean you can actually just download the software, input some lyrics and the melody, and you can use it for serious work. It can speed up your workflow for vocal production. Now, you probably have seen this before, but just for the sake of it, here's a video. I mean, there's probably just some promotion stuff, but.
Amazing grace, how sweet the sound that saved a wretch like me.
So this is the state we're getting, and going back to a little bit introduction, I run a company called Dreamtonics, and our flagship product is called Synthesizer V Studio. Now, the name tells a lot. It's a synthesizer for vocals, and in this software, literally just enter the notes and put in the lyrics and press play, and it's going to sing pretty realistic. So in this talk, if we just, let's say, jump to the results. Now, importantly, the result, not conclusions. The holy grail of this field is to get it sound as real as a human. Now, instead of real, we use it's like more formal term, we call it natural, naturalness. Well, in that regard, how do you measure if some synthetic voice sound as natural as a human being? We do what's called the subjective quality evaluation. Simply words, listening test. Now, on the left side, we have this interface. It's a web tool it's called Beagle.js. You just upload a few, actually a lot of pairs of audio files. You see text atom 1, 2, 3, 4, and each of them is rendered by a different system, and one of them is real. The order is shuffled, so you don't know which has come from which, and we find a lot of volunteers or paid testers and ask them to rate the audio sample quality. And by doing this test, we can get onto a number that represents the perceived quality of an audio sample. And the result is we actually managed to make our system get like a higher naturalness score than a natural speech, like the data we recorded from human, we actually used to train the system. How is that possible? So I'm not showing the conclusion, but in order to get this result, there's some setup we have to go through. Now, let's actually understand this from a statistical point of view. If you're a human, well, all of us are human, then human is inherently random. You ask a singer to sing the same thing twice, to sing the same thing twice, to sing the same thing twice. You see, we have different intonations each time we sing it. That is probably closer to rap, but you got the idea. If you want to make the computer-generated vocal natural, you want to replicate that kind of randomness, or we call it dynamics. So it becomes apparent you need a statistical approach instead of just getting the right answer. You want to get the right range of answers. So there's a bit of a statistical setup here, but each time in the statistical term, we call it sampling. We call it draw a sample. So each time you sing a phrase, it becomes a dot on this plot. There are two axes, for example, the goodness of pronunciation, the goodness of the use of expressions. And each time it could get better, it could get worse. And the goal here is we have a neural network. Each time we run it, we use it to generate like a slightly random, slightly different audio sample. And we want to approximate, we want to make the network generate the same distribution of samples as the human voice. So in the statistical term, it's a distribution approximation problem. Now, there are two ways to, very, very high level, there are two ways to make it sound more human. One is to just pull these two distributions as close as possible. And again, this statistical setup, we call this a generative model. And there are many ways of doing this. But if you go back, in this example, there are only two axes, but in reality, there's like a million of X. It's really, really high dimensional distribution. We won't go too deep into the mathematical details how to deal with it, but I mean, smart people doing mathematics have figured this out like long time ago, and they have things called autoregressive models, generated adversarial networks, diffusion models, which I think you probably have seen the term a bit. We're not going into details here, but I want you to know these are all the methods we use to deal with the high dimensionality we use to make our synthetic distribution as close to the natural distribution as possible. But the thing is, you can get infinitely close, but it can't be the same, or it can't be better than the natural voice. So the second way is to cheat. The simple word is called cherry picking. The statistical word is called rejection sampling. So the idea is to don't try to beat the human at their best. Humans are just too imaginative. They're too good at creating new stuff. So we don't try to make our system better than the best of human, but we just avoid getting beat by a human at our system worst. So one way is, before training, you look at the training data, take out these low quality ones. I mean, humans make mistakes. We're seeing some stuff off key. We could crack a voice. If you see this kind of trend, just remove them from training data, so prevents your system from generating this kind of bad outputs. The other direction is doing, when you're running the synthesizer, you just discard the low quality outputs. So you have someone listen to it. If it doesn't sound bad, just don't show it to anyone, just hide it and run it again. And if you do this like 100 times, you're gonna find the best one. Again, if you talk statistically, you see this plot. You just take out all these orange samples, just keep these green samples. Then, I guess at least all what your system can generate will be falling into the natural range. And if you get enough overlap, you can eventually, shift it closer, and even on average, you can make your system, at least in theory, better than natural voice. So a bit of concrete example how to do that. We can even make it automatic. We can train a neural network to help us to pick the sample that sounds best among all the possibilities. And how you do this is, go from left to right. You generate a few samples with your synthesizer. You present it to a human listener. You ask the human listener to give a rating from 0 to 100. And then you train a classifier to approximate how a human listener would respond to these samples. And then you use this classifier to do the cherry picking for you, so you don't have to listen to 100 times. Now, the hottest topic, if you know ChatGPT, they train their model based on what's called reinforcement learning from human feedback, which are LHF, which is a technique that instead of saving us the need to generate a lot of samples, but infuse that classifier's knowledge of what is good samples back into the synthesizer itself. They do this using reinforcement learning. So we have tried applying RLHF for the model of pitch, and it indeed makes this sound more skillful. For example, you see the better use of vibratos. But the tricky thing is, if you try to apply the error blindly, you end up just getting louder samples. Why? Because calculators just tend to pick the loudest sample as the best sample. If you're training your network, you're trying to make your synthesizer to, if your objective is to try to generate the sample to give the highest rating, then a very easy way to cheat through is just make it louder. Because louder samples correlate to higher ratings. So when you're applying RLHF, you have to be real careful. You do all kind of restriction to the sample to prevent it from, restriction to the model to prevent it from cheating. So we go back here. After applying all these tricks, we upgraded the generative model, we did RLHF, we cleaned our training data, we did a comprehensive test. So in this test, we generated we actually had 20 different sending phrases to generate from. We ran this randomly, matching them with 6 different English voices. We had 100 test participants, each giving ratings to 10 sets of these samples. And And to do it very rigorously, we considered the possibility that people just aren't paying attention when doing the testing. So we actually did a bit of filtering. We actually included one trick sample among the four samples we present in each set. The trick sample is a degraded quality version of one of the samples, and we test if the test participant is able to pick out that trick sample. And if it fails the test, then we just filter out the participant. In this way, there are like 70 of them remaining who contributed useful ratings. We also consider the possibility that humans can do really pitch-perfect thinning. So we actually hand corrected all these natural samples using Melodyne and make sure they're pitch-perfect. And these are reflecting natural corrected group. And the result almost looked too good. I mean, if you look at synthetic sample, you got a rating of 0.55, but natural samples got lower ratings, 0.325. And we can do a statistical testing and find like this difference is statistically significant. So did we got a holy grail? Is it too good to be true? Now, I thought about this for quite a couple of days. I was really surprised at the result. I mean, it's really good looking numbers, but me, myself, the developer, I've been listening to this stuff every day. I even dream about them. And no, I mean, if you just hand me two samples, one natural, one synthetic, I can clearly tell which one is synthetic. So I wonder why people would choose the synthetic sample, at least on average, pick it for the higher naturalness rating. My hypothesis is like some of the technique we're using, for example, RLHF, is really, it is optimizing for preference instead of naturalness. What's the difference between the two? I mean, if we go back to the test, there was actually a test prompt we present to the listeners. We tell them, pick the sample you think is most natural. But that is you think is most natural. It's not we think is most natural. So maybe people just have different definitions of what is natural. And if we talk about different definition for naturalness, then that is already not naturalness, that's preference. So if we use RLHF and or similar techniques, we just go for a preference, maximize the preference, then theoretically it's possible that our system end up in a state that generates more preferred samples instead of more natural samples. And if we fill up this area, then it's possible that we're having samples that are more preferred by human, but not natural. So to test this hypothesis, we designed a second round of learning listening test. This is an A or B preference test. It's directly comparing natural samples against synthetic samples. And very importantly, we added an extra text field. We're asking, why do you think one sample, we don't tell them which, why do you think one sample sounds better than the other? And we ask them to describe in short words. First, the numerical results. This time, we don't have a very clear result on which system sounds more natural, probably because we don't have enough participants. There are only 25 compared to 100, or probably because people will really start thinking more on why one sample sounds better than the other. But I think the more interesting one is we look at the qualitative results. But first, let's actually listen to the samples. This is an example of one of those sample pairs we present to the listeners. This one is synthetic. Oops. I think the audio. Oops. Oops, okay, I'll play it again, sorry. So this one's a synthetic sample. What it would have been, walking in the rain. This one's the natural sample. Walking in the rain. So if we first look at the differences people have mentioned, they said the synthetic sample is more consistent and smooth, but natural sample is clear and crispy. There are other aspects, like if you listen clearly, around this part, the first half of the natural sample, there's a bit of cracking in the voice, which some people describe as bad because these are audio artifacts. And some other people think it's good because audio is audio artifacts. It's imperfection. That's what makes people natural. We also saw some people mention the fewer use of technique is natural. And because natural means don't use too many techniques. But the same exact opposite can be said for natural samples. I mean, it uses more techniques, so it's natural. We also see both set of people mention like better pronunciation. We don't know what is better pronunciation, but better pronunciation is natural. We also see people mentioning the synthetic samples on auto-tune, but it's not shown here, but there are also people commenting natural samples on auto-tune. More specific ones, like good vibratos, I think this is the direct result of RLHF on the pitch modeling, because this particular singer has the habit of singing very, very fast vibratos, which maybe not up to a lot of people's likings, but that kind of got corrected to some extent by RLHF. So I think this pretty much verifies the hypothesis that there's a difference between people's understanding of naturalness. There's a difference between naturalness and preference. So I think we can put it in a nice way, like our naturalness as a developer or as a more behind the scenes statistical thinking people, we think in order for our synthesizer to be natural, it has to be as good as a human, but on the other hand, it also has to model all the imperfections of a human singer. But perhaps by our user definition, what they think is natural is really what they think is natural. So people all have their own understanding of naturalness. Some people may think better pronunciation. Some people can think, maybe imperfection, maybe perfection. The question here, because what we end up testing for naturalness is the actual preference, is there actually a way that we can optimize for naturalness, really naturalness in terms of distribution? And is there a way we can verify that it is indeed going for naturalness, not preference? I mean, we have numerical method. The least we can do is we can do testing. We can directly test the distributions of the audio features, but that hard number doesn't tell how our human ear perceive the sound. Now say, even if we have a way to optimize for the distribution kind of naturalness, should we really do that? Because if we take a stance here, we're already injecting our own bias into optimizing the system. And this is more than, say, just presenting a user with a new option called your naturalness or our naturalness. But we're thinking about high level, where should we steer the future R&D? Should we really go for cranking up the preference score, or should we go for cranking up the naturalness or cranking down the FID or any statistical testing scores? And also, we're a bit in a theoretical crisis. We're wondering if listening tests are useful anymore at this point, because we have already gone past human level in a CMOS test. Now we spent 6 months working on a new generation of algorithm. Now we want to compare it to an old system scientifically, see if it gets better. But the old system already surpasses the natural samples. Say, in this case, if we get a higher score, I guess it means more preferred result, but doesn't tell if it's more natural or not. If we got a lower score than the old system, then there are two subcases. If the score is lower than both the old system and the natural samples, then we know something has gone wrong, or likely has gone wrong, because it is not preferred and is not natural. But what if the score is between the natural samples and the old system? Then I call it the area of unknowns, because it could be more natural, it could be less natural, we don't know. It also led us to wonder if there are better tests than comparative MOS. We know there are tests like Mushra, but that requires a separate reference audio. I'm not going too deep in this area, but I think this is a future direction of research. And it's really interesting because we're not talking about researching how to improve the system, but we're talking about how to work nicely with humans. The last thing is these listening tests didn't cover a lot of things. And also these, what we tested doesn't tell the whole story of singing voice synthesis. Currently, we're only evaluating on the short singing phrases, like the one you just heard, which is 10 seconds. But in production, people use the system on very, very long full-length sounds, 2 to 4 minutes. And within a full-length sound, you could get different voice timbres. You could have like different background music. If you do speech synthesis, there's one thing called Lombard effect, which is, during the breaks, we all go to the excavator room and people are talking very loud. And in that environment, you will actually unconsciously changing your voice to overcome that noisy background. And when we are singing, I'm thinking probably there's a similar effect because if you're covering a song or you have the headphone and you hear the instrumental playing on, would that actually change the way you're singing? We don't know, and we don't know how to model this, and we don't know even if we can model this, we don't know how to test this. Last is, and this one is also really hard to test. When you actually publish the voice as a product to be used in the software, it becomes an interactive experience instead of a passive listening experience like we did in listening test. In that case, this is already like a hugely simplified workflow. Like you record a MIDI, you enter lyrics, you set the parameters, you feel like something gone wrong, and you go back to the previous step and do all these things. And then how do we test how the model responds to the user input? Does it still sound as natural when the user input his own bias into the system? These are all things listening test didn't cover. So at this point, you probably think we covered a lot of things, but they're only questions and no answers, and that's my point. We're in a state where the synthetic results are getting so real that in order to understand, to see what we need to research for maybe next few years of the progress, we need to understand this situation. We need to pick a position maybe, or maybe we shouldn't pick a position on which way to go, natural or preference. So I'll leave the rest to questions and put some nice plots over here. Thank you.
You said that you can always tell the difference between the real voice and the synthetic voice. What are the hallmarks that tell you you're listening to a synthetic voice?
Thank you. Let me repeat to make sure I get it right. So you want to know what are the properties of the voice that enables me myself to tell what is real and what is synthetic. I think that already, that actually overlapped pretty well with these descriptive answers we got from the preference test. In particular, the consistency and smoothness texture of synthetic samples. And also for natural samples, I think, in my own words, I think that is the clarity and crispness probably is better described as more dynamic.
Yeah, so when you talked about listening tests, human listening tests not necessarily being adequate, is that really a matter of the tests themselves or just the subjects that you're actually using in your selection? Could you be more, does it pay to be more selective in who you actually select for these tests?
So it sounds like this is a question about the specifics of the testing and whether the test is carried out scientifically. So a bit more into the background, we carry out a test on a web platform. And this platform allows us to pre-screen the participant based on the background they reported to the website. And in our case, we actually specifically look for musicians who are native speakers of English. There actually weren't a really big candidate pool to start from. There are probably about 3,000 verified candidates are suitable for this task. And we also added that a tricky sample to filter out candidates who aren't paying enough attention.
Thanks for a great talk. I kind of agree that the context of the samples is really important. I think the imperfections don't make sense in isolation, and it's really about the artist's presentation of those imperfections. I was wondering if you've got in the test, you're just recreating the human singing with the synthesis. Couldn't you just kind of have the human sing over a track? And they present that in a certain way, and then the synthesis tries to recreate that, and you test on that. Would that work? Or
so you're asking about a way that we could potentially simplify in the test process, which is to have a human singing a reference track and kind of a back analysis that or convert that into the symbolic music structure and rhythms and compare.
Yeah, and play the backing track underneath both samples when the user listens to them.
Yeah, we actually do have a feature called voice to media conversion. And that is one way we actually use to create these singing phrases. But I think one thing really tricky is you need to be aware of the potential information leak from the natural samples to the synthetic samples. If you don't try to say, we need to do a lot of post-processing like quantization. Otherwise, for example, the timing of the notes and the slight differences in the pitch could be carried into the synthetic sample, making it not completely synthetic. It will be like preconditioned on some human aspects.
Cool, thank you. Yeah.
Hi. Yeah, fantastic talk. Thank you. I was just wondering a little bit in the back of my head, like, in an attempt to assess the naturalness of the synthetic voice that is completely separate from like people's opinions of the quote unquote quality of it. Could you potentially find a way to sort of like give the AI model a portion of the song and then ask it to predictively generate the rest, and then do a difference check, a comparison between the original and what the AI has come out with? That was sort of like completely bypassing the need for a subjective interpretation of it.
So you're suggesting a way. I think it has to do with context, right? So if you provide the AI with the context of the existing song, and then use that to synthesize samples and ask if do the listening test based on the conditioned generation instead of starting from scratch. If that's the case, I think the real question here is not it's not just how you prepare the samples, but also how you do the testing. If you're conditioning your synthesis on this context, you should also present the context to the test participant. But that could be a really tedious thing. I mean, really, if you're doing listening tests, people don't spend that much time for each question. They're not prepared to listen to a lot of context and then make a decision. So I think a lot of things also have to do with whether or not the test can be carried out realistically. And I think that is one of the unsolved challenges.
So just in terms of conclusions you're taking out of this analysis and study, because it seems like a lot of what characterizes the natural voice are the imperfections. And many of those are really then what typically in a production workflow we try to get out of the track, right? So what is really a takeaway of that? Is it you will think about adding those imperfections, or you make a distinguishing feature that the quality is ultimately better suited for production purposes? What are really the learnings here is a little bit the question, to the extent you can share.
So you're asking about what we should do with the audio artifacts category. Should we retain it or should we remove it? And I think first, the setup is that this is a listening test. We're asking people if it's more natural or not, but we're not asking them if you would like to see them in the software. So I think that's actually a very good direction, because there already is a difference between listening test and testing a software itself. And I think in most cases, people don't want it.
Thank you so much. That was a very, very, very insightful talk. I guess I had a slightly off-topic question about the way you guys go about kind of like taking your models and getting them to run efficiently on user hardware. It seems like that's a really tricky challenge, but it seems like something you guys have done exceptionally well. I just wondered if you had any insights you were able to share.
Thank you so much. It goes back many years. When I started working on this, the whole field wasn't so excited about AI stuff. We're rooted very deep in the traditional sense of digital signal processing. And now, I mean, our algorithm had fully switched to what's so-called AI, the deep learning, a lot of like ConvNet and generative models. But really, that early insight of the digital signal processing helped us a lot in making things faster.
Great, thank you so much.
So we do have to wrap up, but we do have one question that's come in online that I think we should just take care of. If we can wrap it up in just 1 minute, that'd be lovely. And thank you for this great talk. The question from online says, thank you for the great talk. How many different singers and different synthetic voices were present in the listening tests?
There are 6, so it's written here. I think 4 female, 2 male. These are all voices are recorded in English.
Okay, thank you. Well, great talk, great technology. Look forward to see what comes next.
Thank you. Thanks so much.